In this video, I will determine the symmetry of the vibration modes of this atomic cluster that consists of 6 atoms. This cluster belongs to the octahedral point group. We have the character table of the octahedral point group here. It's fairly complicated, so you can download this Excel spreadsheet from my website. What you need to do is search for PCAM-CW using Google in any web browser, and the first link is going to be my website over here. And if you scroll down, you can see a bunch of documents under this building physical chemistry from scratch, and you will see some Word files and then Excel files, molecular symmetry, so it's going to be somewhere here. Alright, let's get back to this Excel spreadsheet. This is the character table, and we have 1, 2, 3, 4, 5, 10 different types of symmetry operations. So over here you see 8 C3 rotational operations, Y8. Well, if you look at this structure, it's possible to have 4 C3 rotational axes. For example, there's a triangle here, there's a triangle here. So if we connect the center of this triangle and the center of this triangle, you have one of the 4 C3 axes. Yeah, when you have a C3 rotational axis, you can rotate the structure 120 degrees or 240 degrees. So when we have 4 such rotational axes, there are 8 symmetry operations. And we have other types of operations, and you can see the total number of symmetry operations is 48. So for example, over here we have 6 C sub 4 symmetry operations, so I put 6 here. We have 8 S sub 6 symmetry operations, so we put 8 here. And the 48 is the sum of the number of symmetry operations of each type. And this is also the order of the octahedral point group. We can get the order of the octahedral point group this way as well. If you look at the characters in the column of the identity symmetry operation, you just square every single number. You get 1, 1, 2, 3, 3. Over here you have 1, 1, 4, 9, 9, etc. And you sum up all the squares, you get 48 as well. That's the order of this point group. Now let's determine the symmetry of the vibrational modes. Step 1, we need to determine the number of atoms that remain in the original positions after a symmetry operation. So over here, this is in the column of the identity symmetry operation. That means doing nothing. If you do nothing, all 6 atoms remain in their original position, so you put 6 here. And the second number is 0. Why is that? This is C3 rotational operation. So again, if we look at this C3 rotational axis, and we rotate the structure about this C3 rotational axis, all 6 atoms move away from their original position. Alright, so that's why it's 0 over here. And let's look at maybe one more example. Sigma H. There are 3 sigma H symmetry planes. So over here there's 1 sigma H that cuts this structure into 2 halves. This sigma H symmetry plane contains 4 atoms, atoms 2, 3, 4, and 5. So if we do a reflection with respect to this symmetry plane, 4 atoms remain in their original positions. Atoms 1 and 6 switch their positions. That's why we have 4 here. Alright, this is how we get those numbers. We multiply these numbers by the characters of x, y, and z. So let's look for x, y, and z. You may view x, y, and z as unit vectors in the x, y, and z directions, or dipoles in the x, y, z directions, or px, py, pz orbitals. Anyways, we have the characters here. You can see it's 3, 0, minus 1, 1, minus 1, etc. And we copy that here. Alright, so that's just the characters of x, y, and z. Now we do a multiplication, B17 times B16. Alright, and we'll just do the multiplication over here. And you can see this one is K17 times K16. We got these products. And now we multiply these numbers by the order of symmetry operations. That's just the number of symmetry operations in each type. Alright, so these numbers. Alright, we have 8 symmetry operations that belong to this type. We have 6 symmetry operations that belong to this type. Alright, so we do that as well. And after this multiplication, we get these numbers. So B18 times B1. And over here, this is just K18 times K1. And then we have this row of numbers. We have 10 numbers here. And now we multiply these 10 numbers with the characters for each irreducible representations. Alright, we have 10 different irreducible representations, and A1G is totally symmetrical. So the characters of A1G should be 1 1 1 1 1 1 1 1 1 1. Let's double check. A1G 1 1 1 1 1 1 1 1 1 1. A2G we have some negative ones here and here and here. E sub G, E means doubly degenerate. So you see 2 here. T1G, T2G are both triply degenerate. So you see 3 and 3 here. And by the way, T1G is the symmetry of the rotations of this octahedral structure. T1U is the irreducible representation for the translations. XYZ also denote the translations in the X, Y, and Z directions. Alright, get back to this. We just do some multiplications. We use this 10 numbers, and then for each irreducible representation we also have 10 numbers. Just multiply those together. For example, T2U, it's going to be B$19 over here, this row, multiplied by B13. B13 is over here. This row is B13. These 10 numbers are the characters of this T sub 2U irreducible representation. Alright, we got all those numbers. We sum up these numbers for each row here. For each row, 48 over here, it's for E sub G row or E sub G irreducible representation. 96 for T1U symmetry or T1U irreducible representation. We have those sums, 10 of those for the 10 irreducible representations. Now divided by the order of the octahedral point group, which is 48. We got some integers. These numbers have to be the integers. Alright, they have to be integers. Those are the number of motions that belong to this corresponding irreducible representations. Alright, simply it means we have one motion with A1G symmetry, or irreducible representation. All right, and this A1G means totally symmetric, so you can imagine this corresponds to the symmetric stretching of this structure. Now let's look at these two numbers. You see -1 here, -1 here, because my goal is to determine the vibrational modes. So we need to subtract the rotations and translations. The 3 rotations, they have T1G symmetry. The 3 translations, they have T1U symmetry. How do we know? R sub X, R sub Y, R sub Z, those are rotations, T1G. X, Y, and Z, those are translations, T1U. So that's why I put a -1 here and -1 here. Now we have the symmetry for the vibrational modes. We have one mode with A1G symmetry, one E sub G symmetry doubly degenerate, one T2G symmetry triply degenerate here, and then one T1U and one T2U. So if you sum it up, it's 1 plus 2 plus 3 plus 3 plus 3. And we get the total number of vibrational modes, which is 12, because we have 6 atoms. 6 atoms have 18 independent coordinates and 18 independent motions. And 18 minus 3 rotations here minus 3 translations here, we get 12 vibrational modes. Now what if we have another atom right at the center of the structure? So it's pretty easy. I'm going to show you another picture over here. We have one additional atom at the center. All you need to do is you just need to change this numbers of atoms that remain in original positions after a symmetry operation. So over here, since we have an atom at the center, so this 10 numbers are simply this 10 numbers plus 1. That 1 is from the central atom added right at the center, because when you have a molecule like this, after you add a atom at the center, and then when you count the number of atoms that remain in original positions after a symmetry operations, the center atom never moves. So you just you change this to 7, 1, 1, 3, 3, 1, 1, 1, 5, and 3, and that's why you got this 10 numbers. And then you follow the same procedures. In the end, you get the number of vibrational modes. I need to put vibrational modes here. Alright, that's how we determine the number of vibrational modes for a molecule or a atomic cluster that belongs to the octahedral point group. And you can find this Excel spreadsheet on my web page right here under this building physical chemistry from scratch. You'll find molecular symmetry spreadsheets.